Okay, here's where we left off, and we're going to continue with Chapter 11. I hope everybody had a good Thanksgiving. Um, just a review here again. We're covering sections 4 and 5 topically only, um, and I think I explained this last time, so we'll get on to the next slide. There are some representative catalog data type charts for ball bearings. That's on these next several slides. Next two slides, I guess. One is in, these ones are both in millimeters. I've never actually used a book-based catalog. I usually just go to the SKF website, and they pretty much have a tool there for you. You put in, so I use SKF. Oh, let me do that a little bit better. I use SKF's, and of course I went off the page. SKF's catalog website. I'd call it a software. It's called a website tool. Every time I've ever specified a regular catalog type bearing, it asks you for the dimensions and a couple other specifics, how you want it sealed, temperatures, all sorts of stuff. RPM, static load, dynamic load, and it'll just spit out for you all the bearings in their catalog that fit that description. And you can pretty much just pick the cheapest one or the one with longest life. It's all pretty much well laid out for you there. So this would seemingly be good representative catalog data, um, but you can actually get away with designing bearings without ever calculating an L10 life or knowing what C10 and C0 stand for, even as long as you know what dimensions and loads you have. Pretty much SKF website will will select what bearings are appropriate for your application. But you'd use these charts for any kind of bearing problem that we're going to do. If we have combined radial and thrust loading, we need to find an equivalent load. So that's we have FA is your axial load, and FR is the radial load, and FE, this is the equivalent. God, my handwriting's bad. This is the equivalent radial load for a combined FA and FR. So we need to find an equivalent radial load for bearings that have both axial and radial load on them. It's F sub E. As you can see in the plot here, that the data has two different behaviors, and so to demystify this, there's going to be two different equations for determining FA, and it depends where you are relative to this this point E, which will get explained here in a little bit. The V in this equation here, FE over VFR and FA over VFR. V is the rotation factor. This is in case the outer ring, basically the outer ring, if the outer ring is rotating, then everything inside is rotating faster than if the inner ring was rotating. Sorry, I'm rehydrating here. You can basically approximate the previous chart chart, which is repeated here as two different straight lines. And that's about the crux of this slide. And these are the equations for that. We have a constant. This is the first equation, which belongs to this line. This line is a constant without any slope. And then this equation, which is this line, which now we have a slope. So they've just rearranged this into one equation. Obviously, so the first equation, so this is on the previous slide. This equation applies now to both of them, so they've kind of combined the equations. And this one belongs to that section, and this one belongs to that section. The boxed equation belongs to both sections, and I'm not quite sure why they did this, except it makes it easier to find it in the table here on the next slide. So as you can see, all of these are yeah, they have a FA over CO from the catalog. So CO you get from the catalog. FA is your axial load. From that you get your E, your X1, and your X2. Sorry, X1 or Y1 or X2 or Y2. You can see that in this equation, the way they've combined it, they have Y1 equals 0 if FA over VFR is less than E. So that just devolves down into the straight line again, FE equals VFR. So that's how they combined it. They basically combined, let me go back a slide, 2 slides. They combined these two equations, 1 and 2. So this is 1 and 2. They combined them just to make it easier to look at the table here, because they're eliminating a term, so they're eliminating a term on the table. Again, not quite, and also this is just a 1. So I'm not sure why they did that, but that's the way the book lays it out. But so you have to check. If FA over VFR is less than or equal to or greater than E, and that determines if it's less than or equal to, you'd use these two numbers for X1 and X2, and if it's greater than, then you'd use these two. So the first step 1 would be you check out what your, let me pick a different color here. Check out your FA over CO, determine what E is. So you step 1. Step 2 is find E. So step 1 is FA over CO equals what? Step 2 is find E. Step 3 is what is FA over V. Let me draw that a little nicer and pick the original color. So you calculate FA over VFR, and is that less than or equal to or greater than E, and then pick, based on that, pick I equals 1 or I equals 2 in this equation. Here's I right here. So you'd use I equals 1, you'd use X1, Y1, I equals 2, you'd use X2, Y2. Okay. some bearing life recommendations. Uh, this is what kind of life you would need. And so when you're calculating L10 life and RPM and all that stuff, you'd think that aircraft engines would need a bit more life than that, but they actually just change the bearings pretty regularly. They overhaul those engines, at least in Western countries, modern countries, or any country that isn't buying secondhand planes. They're changing those bearings pretty often. That's why I would be wary of flying these tertiary airlines in out of nations that do not have good resources, and because they don't change those bearings that often, and statistically they're just asking for trouble. And if you read the news, there's very few airliners go down in this country, but they seem to go down a lot more in other countries that, like smaller countries that don't have a lot of resources, maybe kind of poorer nations. They just don't have the same maintenance regimen, and they're not brand new airplanes. They're third hand, fourth hand airplanes. Not and the bearings aren't replaced that often, so along with the blades and everything else, eventually something's going to break, and eventually a plane's going to drop out of the air because of that. So you'd think you'd need longer life, but you don't. They're relying on a good maintenance schedule. And there's other types. So this is a good finals question. How many kilowatt hours of life would you require for machines that have 24-hour continuous service? And as long as you know where to find the table, as long as you've seen it before, it's not a big deal. But if you have to hunt for it, then it becomes an issue. Load application factors, again, so if you have a problem that's has impacts, this is similar to a factor of safety. You just multiply the load by this factor. That's why it's called load factor. So they've got some. It's just a starting point here in lieu of a factor of safety for your bearings. These seem fairly non-conservative. They're all hovering around 1. So if you're unsure, I'd definitely go with a better factor of safety on a bearing. Everything, I mean, that's transmitting all the forces from the shaft to the stationary part. So if you can afford it and it doesn't weigh too much, go with a beefier bearing. Example 11.4. They've got an angular contact ball bearing. This is one of those F equivalent problems. They give you FA and FR. So we have you can list the given. You have FA, FR. So obviously we're going to have to find FE. They give you C0, and they give you C10, and they want you to. And they also give you the bearing type. So you might have to look that up in a table in the back of the book, and then they want you to find the L10 life in hours. And they've also given you the RPM N, which is the RPM. This is the rotational speed. So rev per minute is usually, in case you were not aware, denoted RPM. So when they start the problem here, how did they get V equals 1? Remember, v equals 1 was a speed factor. I think that's way back on slide 17. 16 maybe? Yeah, here we go. So here's where, way back on slide 16, we're on slide 22. They've got a outer ring stationary. So that's another thing they give. So that's the part that makes v equal 1. Now, the first thing they do is calculate, like I mentioned, FA over CO. And from that, they interpolated E. I'm not going to have you interpolate. So just pick the closest value. So in this class, pick closest value. They interpolated. This is a table value, and this is a table value. This is not a table value. So if I put a problem like this on the final, you would have picked 0.28 for E. And you notice that that's not that much different from the E that they interpolated, 0.285. So, for an engineering estimate, that's perfectly fine. Then they go through and calculated FA. So let's make sure I got my steps here. Calculated E. Let's go back up here. Hold on. FA, see step 3 here. FA over VFR. Step 3. So that's step 3. They calculate FA over VFR from all the given. And it's greater than E. So this is E, the E that they found. And so they interpolate again. Don't bother interpolating. If they get 0.8, then you would use this number again. And they're only finding Y2. They don't find X2 because X2 is just a bunch of ones. So if you're looking for the missing information, this is X2, this is Y2. In this case, you just use 1.55 for Y2. And then the design life, they're saying L sub D is design life. L sub D is design life. And they're saying that's equivalent to the L10 life, the life at which 10% of the bearings will fail. And the design force is the equivalent radial and axial load. And so they're using equation 11.3 for the solving for L10. So they're solving equation 11.3 for L10, and they calculate 16,150 hours. So what do we got here? So a couple things, I think I already mentioned this. F sub D is the design load. That's going to be equal to your equivalent load. A equals 3 for ball bearings. Let's not quite sure where I have that in there, but oh, A, right here. This little exponent. So see slide 10. It's different for ball bearings or roller bearings, so it's equal to 3 for ball bearings. So L sub R is in 10 to the 6th revolutions. That goes in the capital L sub R, and this should be a script L. So here's where some of the scripts got messed up. So this should read L sub R equals script R N sub R times 60. This didn't come through right. Same thing here and here. this should be L sub D N sub D 60 equals L sub 10 N sub D 60. And they have the design RPM here as 720 RPM. And here again, this is a mistake. This should be a script L. When I ported it into OneNote, the script, so script L did not make it through to OneNote. So that's all the circled L's should be script L's. Same thing here, should be a script L, should be a script L. L is in hours, so L is in hours. L is in 10 to the 6 revolutions. Again, the special note, you don't have to interpolate, just use the closest value in the tables. That'd be the only thing I would do differently in this example problem. Okay, section 11.7, variable loading. We're skipping this. A couple notes about it though. If you need this level of detail with bearing load, contact your in-house design experts. So ask if they know how to proceed. This is the biggie. Contact the OEM. And if you don't get joy from those, then unfortunately you'll have to research your own answer. But I would say almost 100% of the time, this one right here is going to work for you. Explain to a salesperson, a sales engineer at the original equipment manufacturer what you got going on as far as size constraints, temperature, speeds, and loading, and they'll hook you up. They definitely want to sell you bearings. If you have to research your own answer, you'll probably have to look beyond what a section 11.7 has to answer. And most importantly, we can skip examples 5 and 6 in this chapter. The book also doesn't cover high-speed bearings. So I'm looking at this this right here. Don't screw around with high-speed bearings on your own. Immediately contact the OEM. Sometimes I've had to do this myself. We designed some rolling element bearings to go upwards of 20,000 RPM. Actually, the OEM screwed it up. Well, we actually hired a specialist, even though I'm a consultant. The consultant hired a consultant, specifically a bearing consultant. That's saying something, considering my PhD was related to rolling element bearings, that I realized I was out of my depth with super high-speed bearings, and called somebody who just does that their entire career, retired and now consults. Got 50 years of experience. His name is John Rumbarger. If you want to look him up, if you ever have a really bad rolling element bearing design problem, if he's still alive, John Rumbarger is your guy. At this point, heat removal becomes critical, and you can definitely expect a very limited life out of really high-speed rolling element bearings. And again, roller bearings follow similar catalog rating rules as ball bearings, so we're going to skip example 11.7. A couple slides coming up here. One is different types of bearings. Other than ball bearings, we have tapered roller bearings. So straight roller bearings, the first bullet item, straight roller bearings can't carry axial load. So that's why we have tapered roller bearings. Ball bearings can handle small axial loads. Tapered roll bearings can carry large radial and large axial loads. So these are heavy load bearings. Heavy, radial, and axial load. So if you have a high load application that has both radial and axial large loads, go straight to tapered roller bearings. And Just keep in mind that several figures in the book don't actually show the taper. And sometimes that's actually fairly accurate. The rollers don't have to be incredibly tapered. This is one where they don't quite look tapered, but this is out of the tapered roller section. This is giving you all the details of the what's involved. We have a cone section on the inside. We have the cup as the outside. Usually with ball bearings, you call that the inner raceway and outer raceway. On a tapered bearing, you call that the cone and the cup. So you should be familiar with this. This is the anatomy. So basically, whoops, I got something popping up here on my screen up here. Okay, anyhow, oops, sorry about this. Just be aware be able to find this figure for the final, and be able to identify parts and dimensions on a bearing. But you can pretty much skip example 11.8 through 11.11 and skip the reliability calculations. I was going to blast forth through the whole rest of the chapter, but actually something popped up on my second monitor I have to take care of. So I'm going to call this the conclusion of part 2. And then there's still going to be one more part left for chapter 11. And we will pick it up from here. This is slide 27. There's 10 more slides left, so that's a good third part. So I'll stop here and we'll start again with slide 28.